abnormal pressure, there is something that stops the transfer of fluids from one side to the other, a barrier, if you will. Let's go back to the fish. The water level is fixed by a barrier, but there is still layers of rock over him. He feels the overburdened pressure of the rock, but because the water level is stopped from rising, as it normally would in a simple displacement by a barrier, the fish will now feel increased water pressure. The impermeable barrier prevents the water from squeezing out at the lower intervals, causing the porosity and pore pressure to be greatly higher or lower than expected. It is important for us to know the various pressures of our zones as we drill deeper. Hitting an area of greatly increased pressure that we are not prepared for can be very dangerous. Drillers constantly monitor the downhole pressure for this very reason. In this picture, we have a trapped reservoir with normal pressure. In the reservoir, we have a little bit of oil and lots of water. When we drill into this reservoir, what will happen? Will we need a pump for the oil to flow? Or a pump for the water flow? Or a pump for both? Let's look at what happens when we drill into the water. In this picture, we've drilled into an anticline structure full of water at a depth of 10,000 feet. The pressure at the surface is 14.7 psi. To calculate the pressure of the water at a depth of a 10,000 foot hole, we use the formula, which is pressure equals water gradient times depth, or P equals 0.5 psi per foot times 10,000 feet, to calculate that the pressure is 5,000 psi. Now, inside the pipe, the pressure is equal to the pressure at the surface. So, like with the U-tube, at the end of our pipe, we have a closed valve or door, and when I open the valve in the U-tube, the water will rise because of the pressure differential of 14.7 psi at the surface and 5,000 psi at the valve, which forces the water up. But how high will it go? With simple salt water, it will make it almost to the surface. Let's go back to our U-tube. Again, with only water, what will happen if I keep adding water from one side with the valve open? Both sides would fill to the top, and then it would spill out on the left-hand side. Now remember what happened when I added oil. The level of the fluid on the side with the oil rose higher. Now, if I keep adding water, the side with the oil will gush up and out before it overflows. Let's go back to our reservoir with the same depth and the same pressure at the surface and at 10,000 feet. This time, we put our pipe just in the oil. When we open the valve, the oil will gush out because the whole column of oil will be less than 5,000 psi because oil has a lower gradient or lower density than water. Because the oil is lighter than water, the oil is pushed up and out. How high will the pipe need to be so that it is balanced with the psi from the oil and psi from the water? We really don't care as long as we can get it to the surface. So to answer the question of whether we need a pump to get the oil to the surface, the answer is no. The normal pressure of oil at the bottom of the hole was enough to push it to the surface. Gas will come out even faster because its density is even lower. Now let's look at a reservoir with abnormal pressure in an artesian overpressure. In this picture of abnormal pressure, we have drilled into our reservoir in an anticline, but this time we have an outcrop. It could be 100 kilometers away. In this example, the oil is trapped in a shallow anticline, but outside water from rain is able to penetrate the formation. Let us introduce an energy formula. We need to talk about potential energy of a formation. Pressure is defined as force divided by area, or rewriting, it can be written as energy divided by volume. Or we can, in this case, we're talking about potential energy, PE divided by volume. Now, PE can be written as mgh, giving us an mgh divided by volume. And m divided by volume is defined as density, or rho. So now we get pressure equals rho gh, where g is the gravitational constant and h is the height of the water. The higher h is, the more it is going to push on the oil. This can be very dangerous when you drill into an area of abnormal pressure because it can explode out. This is a good example of artesian overpressure. Abnormal pressure can arise from several methods. Number 1, artesian water flow, which we just showed you. Number 2, deep burial of unconsolidated sediments. Number 3, folding in mountain front areas. Number 4, very deep sandstone burials. And number 5, sealing of pores and chalk formations. Drilling engineers must always be on the lookout for these conditions. These various types of abnormal pressure will be discussed later when we talk about drilling an oil well. In this chapter, we discussed the basics of the origins of petroleum, the basic chemical compositions of petroleum, reservoirs and reservoir rock properties, things like porosity, permeability, and fluid saturation. We talked about the migration of oil from a source rock into a reservoir rock, and what is an oil trap, and types of oil traps, structural and stratigraphic. We also talked about reservoir pressure, the energy to push out the oil. We have normal pressure, which is a function of depth. We have abnormal pressure, which is high overburden pressures. All these topics are important to the petroleum engineers, the drilling engineer who's drilling the oil well, the production engineer who's producing the oil, and the reservoir engineer who's monitoring the oil fields. This is the end of Chapter 2, the overview of the petroleum industry.